Let's spend this video going over another solution stoichiometry problem from soup to nuts, so from the beginning to the end. Okay, so this is everything that you would probably ever have to do in terms of stoichiometry. That's why these problems are really good. So let's start by predicting the products of this reaction. Now, before we even do that, let's set up what is going on here. We have two solutions. One is 65 milliliters, and the next is, and I'll make it a little bit bigger, the next is 180 milliliters. Now, when we mix this, this is calcium nitrate, CaNO3, and then this is aluminum sulfate, SO4, 3. Okay, when we mix these, something should probably precipitate. Okay, and so let's mix them. And so when we mix these things, it's going to be in a separate container, and so we're going to end up with 245 milliliters of some combination of these two. Now, in order to figure out what the combination is, I'm going to make kind of that Punnett square thing. Okay, and this is, let's see, so we're going to take calcium nitrate, calcium ions, 2+, and then nitrate ions, NO3, 1-, and then here we're going to do aluminum ions, Al is 3+, and then the sulfate ions, and sulfate is SO4, 2-. Now these things are floating around in solution, and so we need to know that the positives aren't going to attract to each other. Remember, opposites attract. So these two aren't going to come together, and then the negatives aren't going to come together. What we're going to end up having is aluminum nitrate, AlNO3, 3. And this is important. This number here we want to figure out based on the charges, right? Because what we have is aluminum 3+ and nitrate 1-. Least common multiple is 3, so there's 1 there, and there's 3 there. So that's why this is aluminum nitrate. And then we get calcium sulfate, and we do the same thing, Ca2+ and SO4, 2-. The least common multiple is 2, so there's 1 of each. So this is going to be CaSO4. So that these are the products of the reaction. But now we have to write a balanced molecular equation, okay, based on those products. Well, the balanced molecular equation is going to be fairly straightforward. So I'm going to label that ME for molecular equation. Okay, and we had CaNO3 nitrate plus aluminum Al, let's see, Al2 SO4, 3. Maybe I won't run out of room here. And that gives us the products, which we just predicted. And the products are AlNO3, 3 plus CaSO4. So that is the molecular equation, but we need to balance this and write the states. Okay, so I think the states are a little bit easier. So remember, we're going to look back and we're going to find all these things. We're going to find that this guy is aqueous. We're going to look back at the solubility chart, and we're going to find out that this guy is aqueous. We're going to do the same thing here, and we're going to find out that this guy is also aqueous. Keep in mind that nitrates, those are also aqueous. But sulfates in general are solid. So this is going to be a solid. And to highlight that, I'm going to underline it. Okay. Now, I'm going to balance in blue. Okay, so when we balance these, this can be a little bit tricky, but when we balance these guys, if we have polyatomic ions, we want to keep the polyatomic ions together. We don't want to balance oxygens and nitrogens separately, sulfur and oxygen separately. We want to keep it together because we have sulfates on this side and we have sulfates here. So that makes balancing a lot easier for us. So let's get this going here. So calcium, we have one of each, so that's balanced. But the nitrates, we have 2 on this side and 3 here. So we're going to have to put a 2 here. That gives us 6 nitrates and a 3 there. Now, notice that gives us 3 calciums. So if we put a 3 here, that gives us 3 calciums. And we also have 3 sulfates and 3 sulfates. So that guy is balanced. Okay, so that's a balanced molecular equation. So we've done that. Okay, so now it's saying, hey, write a net ionic equation and don't forget the charges. So in order to get the net ionic, we first have to write the total ionic. And the total ionic can be tricky, but we should take our time. When we're writing the net ionic equation, we want to separate anything that is aqueous into its ions. And because we're asked to balance the equation beforehand, we also are going to take into account the quantities. Okay, so here we have 3 calciums. So we're going to put 3 calciums, and then we're going to put 2 plus, and then the state, aqueous, plus, in here we have 2 nitrates, and for every calcium nitrate there's 2, and we have 3 calcium nitrates, so there's a total of 6 NO3, 1 minus, and this is aqueous, plus, now this 2 doesn't stay with that, that comes out front because there's 2 aluminums, and the charge is 3 plus, and that's aqueous, plus 3 sulfates, SO4, 2 minus, aqueous. So you may ask, why does this 4 stay, but this 3 not stay? Okay, well the 4 stays here because we're keeping sulfate together as one polyatomic ion. And so the polyatomic ion can be treated as one thing that's not going to split up. So the polyatomic ion, sulfate, is SO4, and so we keep all of that together. The 3 tells us how many sulfate ions there are in aluminum sulfate. Okay, so we do the same thing over here. We have, I'm going to end up running out of room. So we have 2 aluminum 3 plus aqueous, plus, now, same thing, we have 3 nitrates in every aluminum nitrate, and there's 2, so we're going to have 6 nitrates, NO3 minus aqueous, plus, now the solid doesn't dissolve, so it's just going to be CaSO4 solid, underline. So that's the total, what we call the total ionic equation. And now the last thing we're going to do is write the net ionic equation. So by writing the net ionic equation, that's going to give us just the things that are going to end up changing. So net ionic equation, we cancel everything that's the same. So there's aluminum. Aluminum is the same. We call anything that gets canceled out of the total ionic the spectator ions. Okay, and then nitrate is also going to stay there. So the net ionic in this case is 3 Ca2 plus aqueous plus 3 SO4 2 minus aqueous reacts to form 3 CaSO4 solid. And we can underline that. Okay, but now there's one more thing. If you look, the coefficients are all the same, 3, 3, and 3. The problem with that is that the most correct balanced chemical equation has the lowest ratio here. So the actual net ionic is going to divide all of this by 3. So we're going to get Ca2 plus aqueous plus SO4 2 minus aqueous reacts to form CaSO4 solid. So that's the net ionic equation. Okay, so there's that. And so now the last thing is going to be, well, maybe not the last thing, but it's going to be do the ICE chart. And then these things can be determined once we have the ICE chart written. So we can do a lot. So let's first determine the limiting reactant. Okay, in order to determine the limiting reactant, we have to now take our equation, our net ionic equation, and I am going to do an ICE chart, and we have to determine how much of each of these we have to begin with. I know that this is going to be 0. But we need to scroll back up here, and we need to see how much of everything we have. So we have 65 milliliters of 3.68 calcium nitrate. So I'm going to come down below here, and I'm going to go 65 milliliters of 3.86? I'm sure you're screaming while you're watching this if I'm not right. Nope, 6.8. Okay, you can stop screaming now. Okay, so this is 3.68 molar CaNO3 2. And so to convert from moles, or from milliliters to moles, we have to use this molarity. This number needs to be in liters. So we're going to go 0. We move the decimal point over 3 spots. And so that's liters. 0.065 liters, X line. And so we're going to put liters on the top, or on the bottom, and moles on the top. Now, 3.68 molar can also be written as moles per liter. So this is 3.68 moles for every 1 liter. And now we can do some math. So I'm going to bring up my calculator. And I'm going to go turn this on, get rid of any of that junk that's there. And I'm going to 0.065 times 3.68. And that gives us 0.239 moles of CaNO3 2. Now notice here that this is moles of calcium nitrate. Our net ionic equation only calls for moles of calcium. So how do we go from moles of one thing to moles of another thing? Well, in this case we're going to use the formula to do that. 0.239 moles of CaNO3 2 X line, and so we're going to CaNO3 2 and then Ca2 plus. So for every one of these, how many of these do we have? And some of you may be able to see this right off the rip, but this is 1 and 1, so this is going to be 0.239 moles of Ca2 plus. So we're going to put this up here, 0.239 moles. Stay, so that's in moles, so that's good. So now we're going to do the same process with with the sulfate. So we have 180 of 1. I get rid of my calculator because it's in the way. We have 180 of 1.09 molar. So 180 milliliters of 1.09 aluminum Al2SO4 3. Okay, so, and I kind of like this because we don't have to do molar masses at this for these, okay? When we're doing solutions, there's really not a lot of molar mass going on, except for maybe if you want to convert to grams. Knowing how to convert, really super helpful. Okay, so 0.180 liters, because we converted this to liters. X line, we want to get rid of liters, we want to go moles. Now remember, molarity can still be written as moles per liter. So this is 1.09 moles for every 1 liter. And now we pull up our calculator, excuse me, 0.180 times 1.09, and that gives us 0.196 moles of Al2SO4 But again, we don't want aluminum sulfate. We just want the sulfate. So we got to go 0.196 moles of Al2SO4 and we want to X-line this. And so we want to get rid of Al2SO4 and we want to just know how many SO4s are in each one of these. So for every one of these guys, how many SO4s do we have? We have 3. Okay. Now I get this. There's a lot going on. This could be a little overwhelming, but that's why I think when you do this on your own, you need to kind of pause and take time to watch the video at your own speed so you can get what's going on. Okay, and so this is 0.588 moles of SO4 minus. Okay, so this is 0.588 moles of that. So now that we have moles, we have to figure out which is the limiting reagent calculation. Now, again, some of you may be able to see it right away, but I'm going to do it like I always do it. I'm going to do the limiting reagent, reactant, same thing, and I'm going to do those calculations right here. Okay. So for calcium, we take how many moles initially we had, and you can see right in the calculator that calculation is right up there, 0.239, and then we're going to divide it by the coefficient in the balanced equation. Okay, so that's going to be 1. That gives us 0.239. Now for sulfate, 2 minus, sorry, not 2 plus. Okay, we do the same thing. We take the number of moles initially, 588, divide by the coefficient. The coefficient was 1, and we get 0.588. Now we pick whichever one is the smaller of the two. This is the smaller one, so that is going to limit our reactants, our reaction to that. So what I'm going to do is I'm going to take this guy and I'm going to box this guy. That way it shows me that this is the limiting reactant. Okay, and so by definition, the limiting reactant is the thing that is used up completely in a reaction. So saying that, we go minus 0.239. Now, this is really awesome because when we have this, as soon as we get this first box, we can calculate here. We can go from here to here and from here to here so that we can figure out how much of everything is left over. So 0.588. Let's see. So in order to go from moles of one thing to moles of another thing, we need a ratio. And so this is going to give us a ratio right here, the balanced chemical equation. And again, some of you may be able to see what this answer is going to be. Maybe not others of you. Regardless, I'm going to do this. And when I do this, I'm going to cross this off. Okay? Anytime I do a limiting reagent calculation, I cross it off after I figure it out, because we're never going to use the limiting reagent calculation. Okay? So we're going to take 0.239 moles of calcium that we've used, and we're going to X-line it because we want to get rid of moles of calcium and figure out how many moles of sulfate we've used. We have a total of 0.588 moles that we could use. We want to know how much we actually need to use, and so that's a 1-to-1 ratio because we're using, again, the balanced chemical equation from up here, 1-to-1. So we're going to come down, and this is why some people are able to do this in their head. Calcium cancels out. We leave moles of sulfate. We end up with 0.239 moles of SO4 2-. So we come up here and we go, we're subtracting 0.239 moles of sulfate. Now, how many moles of this do we need to, are we going to make? Well, some of you, maybe even more of you, have figured out the answer, but again, for completeness, I'm going to do the math here. So we're going to use the limiting reactant, limiting reagent, both same thing, okay? But instead of going to sulfate now, I'm going to go from calcium to calcium sulfate. And so by doing that, I look at the balanced chemical equation and notice that it's 1-to-1, right? 1-to-1, there's no coefficients there, okay? Now, if you don't need to do that math and you can see it, I'm okay with you not showing the math, okay? But this is where we go. So we go 0.239 moles of CaSO4. That's how much is made. Okay, if we used up this, we're going to make this 0.239, so we're going to add that. Okay, so now really the only math that we need to do up until this point is a little bit of subtraction. Okay, so it's let me turn this guy on. So it's 0.588 minus 0.239, and we get 0.349 moles left over. And here we get 0.239 moles of calcium sulfate made. So that's pretty cool. Okay, so we determine the limiting reagent, we determine the amount of moles to begin with, the amount that each is changing, and how many is at the end. So now the last thing that we have to do is figure out how many grams of solid product we have, and figure out what how much excess reactant we have. Okay, well, that's cool. So we're gonna do the mole calculation first. So which one's the solid? Well, in this case, there's only one choice. It's this guy. Okay, so if that's the solid, okay, I'm going to do a little line there, and I'm going to go 0.239 moles of CaSO4. Now, when we're converting from moles to grams, this is where we need the molar mass. So down below, I'm going to do the molar mass, and I do have my periodic table. Calcium is 40.08. Sulfur is, let me get rid of the calculator here. Sulfur is 32.06, and oxygen is 15.999. Okay. So calcium is, I don't know why when I switch the screen it does that, but calcium is 40, and there's one of them. Sulfur was 32.06, and there's one of them. And then oxygen is 15.999, and there's 4 of them. Okay, I guess calcium is 40.08. Okay, so let me call up my calculator again. So I'm going to do 40.08 times 1 is still 40.08 plus 32.06, okay, plus 15.999 times 4. And we get the total of that is that's convenient, 136.136. And the units on that is grams per mole. So we come up here, we start our X line, we're going from see, this is, you get going quick and all of a sudden you make a silly mistake. We're going from moles to grams, And so for every 1 mole of calcium sulfate, it weighs 136.136. And so now we do the math. 0.239 times 136.136. Okay. And then that answer is 32.54 grams of CaSO4. I'm going to take that, I'm going to put that on my IC chart, and I'm going to, because it's not actually part of the IC chart, I'm going to put it down below, 32.54 grams. Okay, and now the next thing is determine the concentration of this that's left over. So that's a molarity calculation. So I'm going to go here, I'm going to do this, and so remember, molarity equals the number of moles over the volume. Okay, well, how many moles of sulfate did we have? Moles of sulfate was 0.349 moles of sulfate over, and so this is where doing the setup at the beginning helps out. We have 245 milliliters, which is 0.245 liters. Okay, so that's how many liters of solution there is. So we come down here, we go 0.245 liters, and so we go 0.349 divided by 0.245, and we get a molarity of the leftover stuff as 1.42 molar SO42 minus. Yeah, that's cool. Okay, so that's that problem, soup to nuts, top to bottom, whatever you want to say, from beginning to end. Answered all the questions, all the parts. So have a great day. Enjoy.